Hello guys, welcome to the DMS online school. In today's video we are going to be learning on a chemistry lesson which will be looking at the chemical reactions. Alright, so this is a very important lesson in chemistry, and in this lesson we are going to cover the entire lesson, which is going maybe to go over an hour. Alright, so this topic actually starts with a subtopic which is the rate of chemical reaction. Alright, so before going into detail of what the rate of chemical reaction is, we must know what the word rate means. So the word rate means how fast something is. Alright, so the word rate means how fast something is. Alright, and then also the word rate also means the measure of how something changes with the time. So it's also the measure of how something changes with the time. All right, so maybe an activity is taking place, then you are measuring how long that activity is taking, then that is actually also rate. And actually rate also means speed. All right, so this simply means then rate of chemical reaction is the measure of the change of the reaction with the time. All right, so rate of chemical reaction is the measure of the change of the reaction with the time. Yeah, so as the reaction is taking place, you must understand that the reactants are reacting to form more products. So reactants concentration is decreasing while products concentration is increasing as time is ticking or is passing. All right, so rate of chemical reaction is the measure of the change of the reaction with time. So scientifically now we define rate of chemical reaction like this. So we define it as rate of chemical reaction is the measure of the change in the concentration of the products or reactants with the time in a chemical reaction. All right, so let's push this one up here. All right, so we can use a formula to actually convert this one. So this statement can be converted into a formula by saying a rate of chemical reaction is equal to then a change in amount of substance over change or over time taken. So change in amount of substance over time taken is actually also rate of chemical reaction. So this change in amount of substance, this one here, can also mean final amount minus initial amount, and then time taken also can also mean final time minus initial time. Now we can simply substitute these into here. So where we have change in time, we put final amount minus initial amount. Where we have time taken, we put final time minus initial time. So let's just push this one up here and then rewrite this equation as the rate of reaction is equal to, then where we have change in amount of substance, we put final amount minus initial amount, minus where we have time taken, we put final time minus initial time, like that. So this one becomes an equation that is used to measure or calculate rate of chemical reaction. All right, so what we should know is that we can measure the rate of a chemical reaction by measuring the following. So we can measure the following to measure the rate of chemical reaction. 1, volume of products or reactants with the time, or volume or mass of products or reactants with the time, or concentration of products or reactants with the time. So if we are measuring change of volume of products or reactants with the time, it's possible for us to know rate of chemical reactions, or we can also measure change of mass of products or reactants with the time to be able to calculate actually chemical rate of chemical reaction, and also measure change in a concentration of products or reactants with the time to be able to actually calculate rate of chemical reaction. Then what you should know here is that the SI units for rate of chemical reaction or for rate of reaction depends in the quantity being used. So it depends. So like if you are using volume, then it will be maybe liters, then per second or per minute. Then here maybe mass, maybe it is in grams, maybe time is in second, then it will be grams per second. Then maybe concentration is in mole per cubic decimeter, then with the time like that. All right, so let's look at this example, which is going to make us understand how a rate of chemical reaction happen and calculated. So here we are going to find out. All right, so we are saying the following experiment is carried out to determine the rate of reaction by measuring decrease in mass of reactant with the time. So actually here there's an experiment that is carried out to determine the rate of reaction by measuring decrease in mass of reactant with the time. All right, so we are saying the following experiment is set up as shown below. So we have this experiment going to be set up as shown, or you are going to see. So we have here some marble chips, hydrochloric acid, conical flask, electronic balance, and then the stopwatch. So let's look at this the procedure. So the procedure says put a flask containing dilute hydrochloric acid on a digital balance and add marble chips, closing the flask with cotton wool to stop any liquid splashing out as shown by the figure below. All right, so then second, record the initial mass of the apparatus while at the same time starting the stopwatch. All right, so what this instruction is saying, put a flask containing dilute hydrochloric acid on a digital balance. So this conical flask, we need to add hydrochloric acid to it and then put it on the balance. So let's add hydrochloric acid to it there. All right, so now after that we should put it on the balance, and while taking note of the mass, because they're saying record the initial mass. So we'll take note of the mass. Here it is 00 before we put this one here, and before we start the stopwatch, which is at 0000 minutes seconds. So after putting that, now we'll put it here. We see the mass here. So after putting it there, the mass is 60. Then let's add this is 80. So after adding calcium carbonate or marble chips, it has gone to 80. All right, so now what we are going to do is to record the initial mass, which is 80, while at the same time we'll start time. So here time must be started, then from there we close with the cotton wool here. Then what now we are going to do is to record the mass of the apparatus after 2 minutes in a table. So the mass of the apparatus here, which is the conical flask together with the hydrochloric acid and the marble chip. So get the table, put it here. Then in one of these columns we'll put time in minutes, then here mass in grams. Then first of all we are told to record the initial mass of the apparatus. So we had 80 here as time at time 0 here, then the mass is 80. All right, then now we need to start the stopwatch. So after the stopwatch is started now, as time passes, now we'll discover that as time passes, 2 minutes passes. All right, then the mass changes to 60. So after 2 minutes 60, because here we are told to record the mass of the apparatus after 2 minutes in the table. So we have recorded after 2 minutes here that the mass is actually 60. Then another after 2 minutes here, the mass is 50. So after another 2 minutes, which gives us 4, the mass is 50 here. Again, after another minute, 2 minutes, which goes to 6, here the mass is 35. So here times 6, 35. Then now it goes again to 8 here the mass is 30, times 8 here mass 30. Then also it goes to 10 minutes here, then here the mass is 25, then put 25, then here it goes to 12 minutes, then the mass is actually still 25. All right, so let's push this one up here and look at what happens next. All right, then they're saying plot the results of the experiment on the graph. So these results can now be plotted on the graph. So let's bring the graph with us here. So we are going to bring the graph here. So we are going to plot mass against time. So a mass should be on the vertical axis, time on the horizontal axis. So we are going to line up the axis like that. So now here on the vertical axis we should have mass, while on the horizontal axis we should have time. Now what is the most tricky part on graphing is actually coming up with a scale, or being able to actually put these values on the graph. Now what makes it simple for you is to notice what is given. Like we are given mass as 80, 60, 50, 35, 30, 25, and then 25 again. So now the highest value you have is 80 and the lowest value you have is 25. And then you have like these lines here, 1, 2, 3, 4, 5, 6, 7. All right, so now if you were to give these like 10, 10, 10, 10, will you get 80? If you say this one 10, 20, 30, 40, 50, 60, 70, 80, you see you'll be able to reach the highest value, because how you choose your vertical axis or your graph is to make sure that what you are plotting must fit in on your graph. Like here we have 25 to 80, so make sure that the values that I should put here, they must be able to accommodate 80 and this lowest value, which is 25. So that's why I said if I were to put every line 10, then this line will be 10, 20, 30, 40, 50, 60, 70, 80. So if I say this is 0, this will be 10, 20, 30, 40, 50, 60, 70, 80. So the way I've put like this, I'll be able to plot these values down here for mass. All right, then what else? It's now time here. So time, again, we are starting from 0 to 12. So this is so easy. Maybe if I say 1, 2, 3, 4, 5, 6, 7, I can't reach 12. So if I say 2, 4, 6, 8, 10, 12 here, you see I've been able to actually cater for 12 here. So this is how actually we do it. Now after putting this information here, now we are going to be plotting like these pairs. This one with 0 with 82, with 64, with 50, then 6 with 35, 8 with 30, 10 with 25, 12 with 25 here. So we'll start with this one, 0, 80. So on the time when you are at 0, on the mass you are at 80, somewhere there. So somewhere there we'll put a dot here, red one. There's a red dot there. Then here 2, 60. So 2 is here. Then 64 mass is somewhere there. So 260 is somewhere there. All right. Then we are going to plot 4, 50. 4, 50, 50 somewhere here. 4 here, 50 somewhere there. All right. Then 6, 35. So this is 6. So if this is 40, guys, all right. So if this is 40, and this is 35, 30, then 35 is in the middle between 40 and 30. That's what you should understand. And you must count this to my small line, which means these to my small boxes here, actually they mean 1 unit. So if you have at 30 here, then 31, 32, 33, 34, 35 here, that's the line for 35. Then 8, 30. So 8 here, 30 is somewhere here. So you put a dot there. Then 10, 25. So 10 here, 20 is somewhere here. Then 25 on the middle there. Then also 12, 25. 12, 25 on the middle there. All right, then after that you draw with a free hand a line like this, a curve like this. All right, so make sure a curve looks like an exponential curve like this one here. Now after you plot, there will be a question like this one, which says which of the results would appear to be incorrect. So of these plotted results here, this one here, we have this one here, this one here, this one here, this one here. Which one would appear incorrect? Like this one through which the line has not gone through, which is actually 4,50. Yeah, so from 4,50.4,50, and they're saying explain your answer. It gave a drastic decrease in the rate of reaction. Yeah, so this one gives a drastic decrease in the rate of reaction, so that's why it is actually upward like that. All right, then some other question like this one, which says why did the mass of the flask and its content decrease? So like when you check, the mass is decreasing from 80, 60, 50, 35, 30, 25 here. So why such a decrease? So the answer is that because carbon dioxide gas which is produced escapes into the atmosphere, the loss of mass equals the mass of gas produced here. So when you get marble chip, which is calcium carbonate, reacted with hydrochloric acid, actually you are forming about 3 products, which are 1 water, then number 2 carbon dioxide, then number 3 azote. So that carbon dioxide escapes into the atmosphere, lowering the mass of the content. All right, so when they say here that why did the mass of the flask and its content decrease, then the answer is that because of carbon dioxide, which is also carbon dioxide gas, which is produced, escapes into the atmosphere, the loss of mass equal to the mass of gas produced. All right, so let's look at another question here, D, which says how does the rate of reaction change during this reaction? So here they're asking us how does the reaction change during this time. So we can say that it decreases as time passes here. So when it is going down like that, it means that the rate of chemical reaction is decreasing as time passes. All right, so now another question says why was the plug of cotton used? Like why was cotton used to close the actually conical flask? So the answer is to stop any liquid from splashing out, and then also to allow carbon dioxide to escape. I didn't add that one there. Also to allow carbon dioxide to escape, because if they use something like a stopper wouldn't maybe allow carbon dioxide to go out of the atmosphere, and that will make measuring the rate of the chemical reaction practically difficult. All right, so another question says how long did the reaction last? So how long did the reaction last is actually looking at here. The mass at 0 was 80, at 260, at 450, at 635, at 830, then at 1025, at 1225. So here 25, it means there was no change. The reaction was still taking place. Carbon dioxide was still being produced from here up to from here, then from here the same mass here. It means it stopped from here. So now at what time did it stop changing? At 10. So now the time actually it took, or how long did the reaction last, is actually 10 minutes. All right, so let's look at another scenario here, another question which says find the average rate of the reaction. So we need also to find the average rate of reaction. So rate is going to be equal to, we are going to say change in mass over change in time. All right, that is also a formula. So change in mass over change in time, because you can know that we started from 80 to somewhere 25, and then from 0 to somewhere 10 there. So we are going to say rate of chemical reaction is equal to So what we are going to do as here is to measure actually mass, which is 35 minus 80. No, you may forgive me guys, here it should have been a 25 minus 80 over, because this is when the mass stopped changing. Here it's the same, so the last point, the point before the other one is where you get. So change in mass is from it's a final minus the initial. So final is 25, here is supposed to be 25 minus 80 over change in time actually from here to here is actually 10 minutes. Then the answer after you subtract this minus that, instead of getting here we got the actual answer negative 5 gram per minute. So here what we should be looking at is this, the actual answer guys is this. So here I said it should be 25 minus 80, all right, equals, then divided time 10, all right, which will be negative 5.5. So here the answer is negative 5.5 grams per minute as the average rate of the reaction. So let's look at now example number 2. So example number 2 here says the following experiment was conducted to determine the rate of reaction by measuring volume of the product formed with time. So the following experiment was conducted to determine the rate of reaction by measuring volume of the product formed with time. All right, so procedure here, we have been told the experiment was set up as shown below. All right, so we have a petri dish with magnesium ribbon, then we have a reagent bottle with hydrochloric acid, then we have a conical flask here. All right, so this is a conical flask. Okay, so we have a conical flask there. Okay, so this is a conical flask. Then we have this one here, which is actually the syringe. Then we have the stopwatch. All right, so here now, this is how the experiment should be set up. All right, so the procedure says put dilute hydrochloric acid in the flask, drop the magnesium into the flask, and insert the stopper and syringe immediately as shown below. So we'll get some hydrochloric acid here. We are going to put it here. All right, that's some hydrochloric acid guys. Then from there we are going to get what? We'll drop magnesium ribbon in it like that. Okay, then after that immediately they're saying you put the stopper and you put the syringe like that. So again, the volume here, this syringe measures the volume, then stopwatch measures the time. So as the reaction goes here, which is actually magnesium reacting with hydrochloric acid, you know a gas is going to be produced, which is hydrogen gas, that is going to start pushing the piston here, and then the volume will be recorded by these values here. All right, so you are going to see how we are going to say. So let's say this is 1 milliliter, 2 milliliter, 3 milliliter, 4 milliliter. Then these small boxes here actually means something else. All right, we are going to see what they mean. All right, so next we are going to record the initial volume while at the same time starting the stopwatch. So what we are going to do is to have time in minutes, then volume in milliliters, then here time 0, then volume we are going to say 0, because that's when the reaction is starting. Then they're saying record the volume of the gas produced after 1 minute in a table. So here we'll be reading after 1 minute, we'll read the volume or put here. After another minute, we'll read the volume. So let's say after minute here, 1 minute passing. After 1 minute, the volume now is supposed to be after 1 minute has passed. So this is actually 0.1, 0.2, 0.3, 0.4. So where it is standing here, it is at 0.4, this line here. So I'll say 0.4. Then again we'll record after another 1 minute. After 1 minute it has moved to there. So this is 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7. So after 2 minutes here, then we'll say 0.7. Then again we'll record again. This stopwatch will go to 3 minutes. Then after 3 we'll count again 1, 2, 3, 4, 5, 6, 7, 8, 9. So it will be 3 here and 0.9. Then we'll allow it to go again to 4 at 4. So at 4 again, this is 0.5, 6, 7, 8, 9, then 1. So this one 4 here 1. Then we'll continue allowing it to 5. 5 here it is at still at 1. So 5 it is still at 1. Then we'll allow it to go to 6. 6, this one has not moved, it is still at 1. So 6 and 1. All right, so now this one has gone. So they're saying plot the information in the table on a graph with time on the x-axis and volume on the y-axis. All right, so what we are going to do is to plot this information on a graph like this one here. Then we are told that the vertical axis here is going to be actually volume. So say volume against time. So this one is volume, this side is time. So draw the line like that. Then as usual, we need to put a scale. So again, when I look at my data, here, for volume, I am starting from 0 to 1. All right, the highest value I have is 1. Then for time, from 0 to 4. So on the volume part here, I have 0.4, 0.7, 0.9, 1, 1, 1. So meaning, what I'm going to do myself is to make sure that I scatter this information. So I have 0 and 1. So if I say this is 0, this part here, then this one may be 0.5, then this one 1, so that this information can also be scattered and widespread. All right, so 0, 0.51. So these will be able to be scattered for in here. So now if this is 0.5, then 2 boxes here represent 0.1, like 0.1, 2. I've covered 2 here. So 0.1, 0.2, 0.3, 0.4, 0.5. All right, so it is actually making logical sense. Then here on a time from here, it is so easy. We have 0 to 6, so I can say this is 0, 1, 2, 3, 4, 5, 6. Then I'll begin plotting 0, 0. It's actually here, 0, 0. Then here 1, 0.4. So 1 is here, 0.4. So where is the 0.4? We'll say 0.1, 0.2, 0.3, 0.4 there. Then here 3, 2.7. So 2 is here. This is 2, 0.5. So if this is 0.5, 0.6, 0.7, somewhere there. Then here 3.9 will come to 3 here. So if this is 0.5, 0.6, 0.7, so same 0.8, 0.9 here. Then here 4.1. So 4.1, 1 is here, this one here. Then here also 5.1, 5.1 is here, then here 6,1 is actually 6,1 is here. Then from there we draw a smooth line like that. All right, so now let's look at the question that are there. So this question says find the rate of a reaction at 2 minutes. So you come to the time at 2 minutes here, you come here, they want you to calculate the rate of reaction. Now since this one is a curve, it's hard to go direct like that, so you need some technique. So you put the formula here, rate is equal to change in volume over change in time. So what we do here, actually we draw a gradient at this point where we are being asked to find the rate at. So at the point at which we are going to find the rate, we are going to draw a tangent to it. A tangent is a straight line that touches the same point like that. Then after we do that, we draw like a triangle like that. When we make a triangle, then we'll consider from here to here. One side of the triangle, this bottom one, from where it is starting to where it is ending as change in time. Then from where this line here to where it is ending top here, change in volume. So we are going to say then equals change in volume. We are going to say this top part here. Okay, so this top part here, this top part here, which is at actually 1, minus this down part here, which is actually 0.5. So say 1 minus 0.5 divided by, then here we'll say this line here, which is at 3.2 minus this end point here, which is at 1.2. So say 3.2 minus 1.2. Then after you manipulate, you have actually here 1 minus 0.5, you get 0.5 minus 3.2 minus 1.2, you get actually 2. Then after you divide, you get that it will be 0.5 milliliters per minute. So remember, volume is in a milliliter, then time is in a minute. So these will be the units, 0.25 milliliter per minute, and this will be actually the rate of chemical reaction at 2. Alternatively, this one can be found in another way like this. All right, so what you can do to find this one again, you can just say change, like if you are here, you must know how much volume was produced at 2. So the volume produced at time when is 2 is not found by going to this one here. Then you find it and then say I have found it. It is not going to be the 1 because it will be accumulation of volume. So for you to know how much was produced after 2 minutes, you must actually come here. After you come here, then you make sure that you read the volume here. So when you go this side, the volume is what? If this is 0.5, then this is 0.6, 0.7 upon this line. So you are going to say change in volume from this point to this point. So actually from this point to this point, so here it is actually at 0.7. so you say 0.7 minus at this point is at 0.4, then over, then also you take time at this point. When you come here, the time is 2. When you come here, the time is 1. So you say 2 minus 1, then you say 0.7 minus 0.4, you get 0.3 over 2 minus 1, 1. You divide 0.3 divided by 1, you get actually 0.3. Then you put milliliters per minute. All right, so another question says find the average rate of the reaction. So average rate of reaction is given by equal to, you say total volume divided by total time. So total volume produced here, you started from 0, 0.4, 0.7, 0.9, 1. So it went to 1, 1. So meaning here where it is going 1, 1, it means the reaction ended. ended. All right, so here now it's going to be total volume, excuse me, is going to be 1. So you're going to say equal to total volume 1 over total time again from 0 to where the volume stopped changing. So from 0, 4. So time is 4. Then you divide 0.4, 1 divided by 0 by 4, you get 0.25. All right, so another question says, how long did the reaction last? So the reaction only lasted from here up to here. When the curve starts going horizontally straight, meaning the reaction has stopped. So the reaction lasted from here up to this point when it started going flat. So when you come down here now, you find that the time is 4 minutes. So how long did the reaction last? 4 minutes. All right, so another question says, how does the rate of reaction change during this reaction? So how is the rate of reaction changing during this reaction? So it is actually decreasing. So you can say it decreases with the time. All right, so to add more, we are saying it is highest at the beginning of the reaction and lowest at the end of the reaction. Yeah, so this is actually practically true. Rate of reaction actually increases at the beginning because you have a lot of concentration of reactants, and then actually decreases as the reaction proceeds to an end because the reactants could have finished. All right, so let's say, how now do we know that the reaction should be fast? All right, so here if you drew a tangent at this point, at this point, at this point, at this point, you'll find that each time a point is above the other one is given a tangent, that other tangent at the top seems to be more or less steeper than the previous one. So like this one here is more steeper than this one here. This one is actually less steeper, this one less steeper, and this one less steeper. So what you should understand here, guys, is this, that the steeper the gradient, the faster the rate of the reaction, and vice versa, meaning also if the gradient is less steep, then the rate of reaction is actually also slow. All right, so now the same way, if we drew another one curve like this, so we call this one reaction A, this one reaction B. So the question can be, which of these two actually is more fast? So the one with a steeper gradient between this reaction A and B, the one with a steeper gradient is the reaction which is the fastest. So in this case, reaction B has got a steeper gradient, so it is faster than this one. So we can say reaction B is faster than reaction A because it is steeper than reaction A. So that is what you should know. And when the curve goes horizontal like that, it means the reaction actually has ended. Now, let's look at what is known as the collision theory and chemical reaction. So what does it say? So collision theory states that for a reaction to occur, the particles of reactants must collide with sufficient energy. So this is the collision theory, which states that for a reaction to occur, the particles of reactants must collide with sufficient energy. So let's say we have these particles here of hydrogen atoms here. So when they are reacting maybe to form hydrogen gas, these must collide like that. All right, so now these have failed to collide, these have collided and joined. All right, so that reaction to occur unless these particles actually collide. So what is also said here is that collisions which results into a chemical reaction or formation of products are called successful or fruitful collision. Like this collision for these two, actually it is a fruitful collision because it has made hydrogen and hydrogen join to form hydrogen molecule, but this one was not fruitful because the two of them after actually colliding with each other, they did not actually bond to form a reaction, a substance or a product. So collisions which results into a chemical reaction or formation of products are called successful or fruitful collision. All right. Then what you should also know is that the minimum amount of energy required by particles of reactants to bring about successful collision is called activation energy. All right. So particles also, they need that energy to move with, so that when they collide, then a reaction happens. Now that energy which particles require so that when they collide they make a chemical reaction, that energy is what we call activation energy. And that's why we are saying the minimum amount of energy required by particles of reactants to bring about this successful collision is called activation energy. So what you should understand is that activation energy is used in breaking bonds of reactants and forming of new bonds in products here. So this activation energy, what it does, it is actually it is actually used to break bonds of reactants and then forming new bonds in products. So in other words, activation energy is defined as the minimum energy required to enable chemical bonds to break and the new ones to form. So activation energy is actually defined as the minimum energy required to enable chemical bonds to break and the new ones to form. So for instance, if you have this one as hydrogen gas and this one as oxygen gas, they must actually, if they are reacting to form maybe water or any other substance, so these bonds must be broken and the new one must be formed like this. So this one, the bond here, let me reverse. So this one bond is broken, and here when it is broken, this one can bond like that, and this one can bond with any other oxygen that may be available. All right, so that's what you should understand. So activation energy is defined as the minimum energy required to enable chemical bonds to break and the new ones to form. All right, so let's now look at the energy. So the energy possessed by a bond or by chemical bonds or overcome by activation energy is called activation energy barrier. So that energy which is actually in compounds, I mean that energy actually which is in bonds of compounds, molecules, is what we call activation energy barrier. Therefore activation energy is equal in magnitude with activation energy barrier. So let's look at the profile of this energy profile of these reactions here under collision. So let's say we have a vertical axis, horizontal axis. On the vertical axis represents energy, on the horizontal axis products. So we can actually start plotting here by saying if this is 0, then if these are products here, because something cannot have actually basically 0 energy. So products have got some energy somewhere here, then these products here can actually find it difficult to react, so they need energy here for them to go up there, react, and then form a product here and label it like that. All right, so now from here what you should understand is that the level from here up to the topmost here, this level from the reactant position to the topmost of this reaction progress, this energy difference here is what we call activation energy barrier or just activation energy. Then from here going downward here is what we call overall energy change. All right, so what now we are going to look at is that reaction paths for exothermic and endothermic reaction. Now let's look at the reaction paths for exothermic and endothermic reaction. So we are going to have a reaction path for an exothermic reaction. So their type of chemical reaction, endothermic and exothermic. And endothermic is a reaction which absorbs heat from the surrounding, while an exothermic is a reaction that releases heat to the surrounding. So now what do these or how do the energy profile look for exothermic and the endothermic reaction? All right, so what you should understand is that if this is the energy profile, energy here, so it will be like that. Okay, reactant, product, then here the line, here the line. So this one will be activation energy. All right, so you can notice that reactant are at a line, at a higher line than products. So meaning for these reactants, when they reacted, they even lost more energy, such that the product which were formed were at a lower energy level, and because of that, this reaction is exothermic, and we say reactants have more energy than products here. All right, so let's move to another one here where we have reaction path for endothermic. So endothermic, again, we draw the energy profile like that. Okay, so then this one here will be actually the difference in energy. So this one will be activation energy. All right, so here again you'll discover that reactants are at a lower energy while products at a higher energy. So this means products have more energy than reactants. So this means that they also gain some heat from the surrounding. All right, so let's continue with our revision. All right, so now let's move to the other part here. We are now going to look at factors that affect the rates of chemical reaction. So the factors that affect the rate of chemical reaction. So what you should know, guys, is that reaction rates depends on the collision theory. All right, so reaction rates depends on the collision rate of the reactant particles and the energy of these particles. The following are the factors that affect rates of chemical reaction. Number 1, concentration of reactants. Number 2, temperature of reactants. Number 3, pressure of reactants. Number 4, size of reactant particles. Then in number 5, catalyst. All right, then we have also light intensity. All right, so these 1, 2, 3, 4, 5, 6, these are the factors that affect the rate of chemical reaction. All right, so now let's look at phase concentration and learn how concentration affect the rate of chemical reaction. All right, some concentration here we are saying when the concentration is increased, the rate is increased, and vice versa. So when you increase the concentration, then the rate of chemical reaction also increases. And when we say vice versa, it means when you reduce concentration, then the rate of reaction also decreases. All right, so we are saying, why is it like that? We are saying increasing the concentration of reactants increases the number of reacting particles per unit volume. So the collision rate will increase as well as the rate of reaction. Meaning, for instance, if you have particles that are scattered like this, not concentrated, and others that are concentrated like this, here they will not react faster, but here they will react faster. And the reason why they will react faster is that you have more particles which can quickly collide with each other, and then the reaction will go faster. So like here, if they are to collide, these will collide faster than these, as you can see. So this, because they're closer to each other, so they'll have to collide faster than these. All right, then we are saying concentration affects only reactants in aqueous form. So only reactants in aqueous form are affected by concentration. So let's look at another factor of concentration, rate of chemical reaction, which is temperature. All right, so we are looking at temperature as a factor which affects the rate of chemical reaction. All right, so we are saying when the temperature is increased, the rate will increase and the rate will decrease when temperature decreases here. So when you increase temperature, the rate will increase and the rate will decrease when temperature decreases. So for instance, we have this here. So here we have some heat and here some reactants. So notice what happens if we increase heat. So if heat is increased, even here there is more something popping up. All right, so let me just reverse. Okay, when there's a big flame, you have seen even inside the reaction is going faster. So what we are saying is that this is because particles gain kinetic energy and move faster and collide effectively. So another factor is pressure. So when pressure is increased, the rate of reaction also increases. So this is because the volume reduces, forcing the gas particles closer together and collide effectively. Yeah, so pressure actually makes particles come closer together and then collide. So let's say we have a cylinder here and a piston inside it, and we have some particles here. So if this one is decreased like that, particles will be very close to each other and they'll be able to collide, and the reaction will take place faster than when it is like this, because they'll take time to collide. But here they'll collide quickly because they're closer to each other, and then the reaction will go faster. Then here, guys, what you should know is that the pressure only affects reactions involving gases here. So the pressure only affects reactions involving gases. All right, so another factor, guys, is actually size of reactant particles. Size of reactant particles also affect rate of chemical reaction. So what we are saying here is an increase in the surface area of a solid reactant results in an increase in the number of collisions, and this results in an increase in the number of successful collisions. A fine powder has a larger surface area than a single lump of the same area. In the powdered metal, many more atoms are exposed, so the chance of a collision increases. Yeah, so like when you are using calcium carbonate or marble chips, if you are using a lump, it will be slow, but if you are using powder, it will be faster. And the reason why it will be faster is that because more particles are exposed for the reaction, and because of that, more will collide and the reaction will go faster. So if you have big lumps like this, the reaction will be increasing as you continue cutting them. When you have powder, the reaction will be even faster. So this only affects reactions involving solids. So size of particles occurs or affects only a reaction that is using reactants in solid form. Then the other factor is actually catalyst. All right, so a catalyst is a substance which can alter the rate of a reaction without being chemically changed itself. So yeah, a catalyst is actually a substance that is able to change or alter the rate of a chemical reaction without itself being changed. All right, so what you should understand, guys, is that a catalyst, how does it work? A catalyst increases the rate of a reaction by providing an alternative path or reaction path which has a lower activation energy. If the activation energy is lowered by using a catalyst, then more particles will get over the activation energy barrier much faster, resulting in more fruitful collision to produce products as at a given time. So this one is like this. If you have an energy profile like the one we had, if without a catalyst, maybe a reaction can follow this activation energy here without a catalyst. But if you use a catalyst can provide an alternative energy profile that uses less activation energy barrier, and because of that, the reaction can go faster than when without activation energy. catalyst. Then another factor, guys, is actually light intensity. So light intensity, guys, affect also the rate of chemical reaction. So we are saying when particles absorb light energy, the energy can be used to break bonds, overcoming the activation energy of the reactions and causing a chemical reaction to occur faster. So reactions which occur as a result of absorption of light are known as photochemical reactions. So yeah, there are reactions like photosynthesis, which requires the light energy for them to occur. So such reactions are called photochemical reactions. So light intensity also can cause photosynthesis to go faster or slow. So we are saying the following are examples of photochemical reaction. Number one, photographic film. Number two, photosynthesis. Number three, reactions of halogens. So let's start with this one, photographic film. So how does light intensity affect the rate of reaction in photographic film? So what you should know, guys, is that silver 1 bromine layer coated on photographic film breaks down when exposed to light, exposing tiny dark particles of silver on the film. Yeah, so what we are saying here is this, guys, that in a photographic film there's actually a layer which is actually silver 1 bromine. So this layer is coated on a photographic film, and when a photographic film is exposed to light, then actually this bromine 1 silver 1 bromine actually splits. All right, so when it splits, this is what happens. Now this is silver bromine plus, as it splits now because of light, to give us silver plus bromine there. All right, so and balance an equation by putting a 2 there. Then also, guys, what you should understand is that here also you put a 2. So another one is actually reactions of halogen. We are not going to look at photosynthesis because it's so common. So reaction of halogen is a reaction also which requires light intensity. For instance, chlorine reacts with hydrogen to form hydrogen chloride. So this reaction is shown is slow in diffuse light, vigorous and explosive in bright light. Yeah, so meaning that halogens like chlorine and the hydrogen actually can react to form hydrogen chloride. So that has been stated clearly. Then this reaction is slow. So such a reaction usually is slow in a diffuse or less light, and vigorous and explosive when there's light. So here, guys, you must know is that the equation now is going to be chlorine then plus this hydrogen, which will give us over light, which will give us hydrogen chloride, and a 2 there. Okay, excuse me. So let's push this one up. So now we are going to look at methods of controlling rate of chemical reactions. So these chemical reactions must be controlled. All right, so what you should know is that, as seen already, increase of the factors which affect the rate of reactions increase the reaction. Yeah, so when you increase temperature, you increase pressure, you increase either volume, you increase pressure, you increase concentration, you increase temperature, surface area, all those things, when they are changed and increased, the rate of a reaction increases. So then what does it mean? So we are saying in some cases this can lead to dangerous fast reactions which can result into explosion. Yeah, so in some cases, because of these factors we know about concentration, temperature, then what else are we talking about? Concentration, temperature, surface area, pressure, light intensity. All these can, in some cases, can lead to dangerous fast reaction which can result into explosion. So such explosion occur in flour mills. Yeah, so the flour mills, those mills which actually make flour, where flour has large surface area, because flour is in tiny particles, smooth particles. Because of that, it is able to catch fire. So what we are saying is that increase in flour dust in the air can cause explosion from a simple spark from a machine. So that can happen. So those flour mill can actually have explosion, and those explosion can come about if it is an increase of flour dust in the air, and because of that increase, any spark can cause an explosion. All right, so also in coal mines likewise, can experience an explosion with the increase in concentration of methane in the air, because a small spark is enough to set the mixture of methane and air into an explosion. Yeah, so equally in coal mills, where methane is also one of the things that is produced there, is that if there is more methane in the air, it can mix with the air, and then any spark, it can cause an explosion. All right, so now such reactions can be controlled by reducing frequency of collision, by increasing ventilation and other factors. All right, so guys, this has been a very long lesson and a complete lesson on rate of chemical reaction. So I hope you have enjoyed this lesson, guys. See you in the other lesson. As for now, bye.